This video is on gas law calculations. So we've talked about ideal gas law equation, right? We've got pressure, times volume equals moles times R times temperature, right? With R being that constant, moles, temperature, pressure, volume are all variables for one gas at one point in time, right? We also got that equation from, right, this. Right? They will always equal that R, that same value. Okay, now we've also talked about the individual gas laws. If I go back to here, where we had, right, each one has two variables and they have a relationship. Like if the pressure goes up, the volume will go down. That's Boyle's law, right? The other three are direct with Charles with volume and temperature, either both increasing or both decreasing. Gay-Lussac's pressure and temp, both increasing or decreasing, and same with Avogadro's with volume and moles. So now, instead of just like one at a time, like if the volume goes up, the moles go up, what if we have a gas where we actually want to calculate how much it goes up? Okay, so when we have a variable change, we can calculate it mathematically. So the variables multiplied and divided still equal R. So we can take this every time with pressure, volume over N and T, right? It equals R. We'll say for at one point in time, we can measure all of these for a gas. They're going to equal R. Okay, and then what if they change? If the pressure changes, the volume changes. If the volume changes, the moles change, right? If the volume changes, the temperature changes, etc. And we've got new pressures, new pressure, new volume, new moles, new temperature. But here's the thing with these new ones, they still equal R. So if these two are the same, could we then say, right, that these are also the same? Right? If they both equal R. So then could we take those two and say, well, the pressure and volume all at this first time would also equal the pressure and the volume, or the moles and the temperature of the second time. So we can use this right here to look at variables in a problem. Okay, so what we're going to do is we're going to use variables in the problem, like the problem right here given, and ignore the constants. And by constant, I'm meaning things that don't change, stay the same. All right, so we'll do two examples. So it says a sample of gas occupies 10 liters at 114 torr and 27 degrees Celsius. Calculate the pressure if the temperature is changed to 127 degrees Celsius while the volume remains constant. So we know the temperature is changing. Okay, so let's kind of underline and label what we know. 10 liters, that's a volume. 114 torr is a pressure. 27 degrees Celsius is a temperature. Now these are all together at the same time, right? At this and this. So I'm just going to put ones by all of these. Okay, calculate the pressure. All right, so this is what our unknown is. If the temperature is changed, so we've got a new temperature. So this is T2, we're going to call it, right? It's just different, okay? This is the pressure at that temperature, so I'm going to write 2. And the volume is constant. So V2 equals the same one, is still 10 liters. So when I say ignore constants, that means this doesn't matter. This doesn't factor into anything. So we're looking at a problem where we have pressure and temperature, right? At one point in time, the temperature changes, what happens to the pressure? Okay, so if we've got pressure and temperature, we have a Gay-Lussac's problem, okay? So this is Gay-Lussac. And Gay-Lussac has a direct relationship, right? So the temperature, we can see if it's going from 27 to 127, the temperature goes up, okay? So if it's direct, what should the pressure do? Hopefully you're saying to yourself right now, it should also go up, right? If one goes up, the other goes up. That's what direct means. So our pressure should be a higher value than this 114 torr. All right, so now we can go back to this equation that I wrote up here in green. And we're going to ignore the things that aren't involved in our problem. And we're just going to deal with the ones that are. So for example, what I mean is pressure and temperature are in our problem. So we're only going to write pressure and temperature in our equation. So our equation is pressure over temperature. Notice I'm just not writing the N and the V. And then over here, also pressure and temperature. And look at what we know. We know P1, we know T1. We don't know P2, but we know T2. So this is what we're solving for. We should have one unknown and three knowns. All right. So like I said before, you can plug your numbers in and then solve for P2, or you can do the algebra first with the letters. My preference is do it first with the letters. So I'm going to cross multiply. So this would be P1 times T2 equals P2 times T1. And now I'm going to solve for P2, right? That's my question mark. I'm going to move T1 to the other side by dividing both sides by it. So I get, I'm going to rewrite this as P2 equals P1 T2 over T1, right? This equals all of this. And now I'm going to put my numbers in. So P1 is 114 torr. Now we don't have to actually change to kilopascals here. We only have to do that for the ideal gas law when we have R. We do, however, have to change temperature to Kelvin. So before we plug it in, let's do that. Celsius is 27 here, plus 273 gives me 300 Kelvin. And 127 plus 273 is 400 Kelvin. So 114 torr times T2 times 400 Kelvin divided by T1, which was that 300 Kelvin. So unit-wise, Kelvin divides out. Torr is the units I have left, so that's the unit for my answer. So 114 times 400 divided by 300 gives me 152 torr. Now, before I circle this and say I'm right, I want to make sure I got the relationship I thought I would get. The temperature increased, so the pressure was supposed to increase. Is 152 an increase from 114? Yes, it is. So this is the answer. All right, let's do one more. All right, so it says a sample of gas has a volume of 460 milliliters when measured at 35 Celsius, 740 millimeters of mercury. What volume in milliliters will the gas occupy at same temperature and 175 millimeters of mercury? Let's label. All right, 460 milliliters. This is a volume when measured at 35. This is a temperature. And 740, we've got millimeters of mercury, so this is a pressure. These all go together, right, when measured at this and this. So I'm going to write ones by all of them. It says what volume in milliliters? So here's my question mark. Okay, and so this is my new volume. Same temp. So do I care about the temp? Nope, doesn't change. Ignore constants. Pressure is now this. So P2 is this. So I check, are my pressure temperatures, units the same? Yes, they are. Do I have to convert the Kelvin, the temperature to Kelvin? No, because the temperature is not a factor. Volumes in milliliters. I want it in milliliters. I don't have to change that. I only have to change temperature. All right, so if I go back to here, right, we've got our equation right here in green, right? We're dealing with pressure and volume. So it's these two. I'm going to ignore N and T. So P1 times V1 equals the same thing on the other side. So now I am solving for V2. So I'm going to divide both sides by P2 so I can get V2 by itself. So V2 equals P1 V1 over P2. And now I'm going to plug in my numbers. So I'm going to get P1, which was 740 millimeters mercury, times V1, which is 460 milliliters, all divided by 175 millimeters of mercury, my P2. And my units, millimeters of mercury, divide out. I'm left with milliliters. That's good. Before I finish, which gas law is this? Take a second, check back and look. Pressure and volume. This is Boyle's. Okay. This is the inverse relationship. So I go through and I say, okay, let's see, inverse. Let's see, the pressure goes down, right? It went from 740 to 175. So the pressure decreased. So the volume should increase. So let's make sure it does. So 740 times 460 divided by 175. You should get 1,945.14 milliliters. The volume increased just like we thought. So this is our answer.